Our current understanding of the nature of sound has evolved over millennia and has involved the contributions of numerous philosophers and scientists. In ancient Greece, fundamental notions of sound being related to a vibrating source were noted by Pythagoras. Aristotle observed the mechanical properties of sound. His writing indicates that he may have begun to grasp the longitudinal nature of a sound wave. He notes the air is set in motion by contraction or expansion or compression. Galileo Galilei is often credited with being the first to theorize that sound traveled in a wave form. In his 1638 book, Dialogue Concerning Two New Sciences, Galileo writes that the undulations of a medium are widely dispersed about the sounding body is evinced by the fact that a glass of water may be made to emit a tone merely by the friction of a fingertip upon the rim of the glass, for in this water is produced a series of regular waves. Following the Enlightenment, inquiries into the nature of sound were enhanced using scientific experimentation. In the mid-17th century, Marin Mersenne empirically measured the speed of sound to an accuracy within 10% of modern values by measuring the time of returning echo from a known source. In further experimentation, Mersenne measured the frequency of a specific pitch by studying the oscillation of a rope under tension. Further experimentation in the 17th century by Robert Boyle revealed that sound waves must travel through a medium. Boyle constructed a simple air pump connected to a glass bell jar to create a vacuum. He noted that the sound of a bell in the jar faded away as the air was removed. Once the physical properties of sound waves were more thoroughly understood, scientists in the early 20th century began to apply this information practically. In 1917, Paul Langevin was the first to use high-frequency waves in underwater location. He was also the first to note the biological effects of ultrasound. He noted fish placed in the beam in the neighborhood of the source of the operation in a small tank were killed immediately, and certain observers experienced a painful sensation on plunging the hand in this region. During World War I, the urgent threat of German U-boats led Langevin to apply his echolocation research to the development of sonar technology. He created a sound-generating device using a quartz crystal and two metal plates, which is widely considered to be the prototype for modern ultrasound devices. Sonar technology continued to expand throughout the early 20th century in response to the proliferation of submarine warfare. However, in 1942, it was Carl Dusek who was the first to use ultrasound as a diagnostic medical tool. Applying the advanced sonar technology, he attempted to find brain tumors by analyzing ultrasound beams as they passed through the skull. Dusek created what he called ventriculograms, or images of the ventricles of the brain. He used two opposing ultrasound beams operating at 1.2 megahertz and 1/10 of a second pulses. The patient's head was immersed in water, and variations in the amount of the beam passing between the transducers was recorded as spots of light onto heat-sensitive paper. Modern science has demonstrated that sound is composed of longitudinal mechanical waves. Longitudinal waves are composed of areas of compression and rarefaction. Compression is the portion of the wave where the particles are closest together, and rarefaction is the portion of the waves where the particles are furthest apart. There is decreasing pressure during rarefaction and increasing pressure during compression. Imagine a slinky as your longitudinal wave. Portions of the slinky where the coils are tightly close together with little space between them is known as a compression period. The portion of your slinky where the coils are greatly spaced apart is known as the rarefaction period. Can you spot the areas of compression and rarefaction in this image? One compression rarefaction cycle is equal to a wavelength. Frequency and wavelength have an inverse relationship. As your frequency gets higher, your wavelength gets smaller. This relationship explains why higher frequency transducers produce better axial resolution in ultrasound. Here we see the relationship between wavelength, frequency, and axial resolution demonstrated in a phantom. As you can clearly see in the phantom, as the frequency increases from left to right, so does the axial resolution. This is because as the frequency increases, the wavelength decreases, and our SPL decreases as well. Axial resolution is the result of the SPL divided by 2. Here you can see how better axial resolution allows better visualization of cardiac structures. Here we can see how a higher frequency transducer on the right allows better visualization of the musculature of the hand. Here you can see how choosing a higher frequency transducer as well as a better imaging window visualizes a fetal heart more completely. Just like bats and dolphins use these high-frequency sound waves to navigate through space, we can also use them to navigate through the body. We can continue to be the eyes for the doctor thanks to the great advancement and discovery of the physical components of the sound wave.